Hello and welcome to the final concluding lesson on straight line graphs. This is the fifth and final one before we move on to having a look at circle geometry. So we've done pretty much all we need to. This lesson though is going to focus on using the skills we've now developed to model real life and contextual problems which can be shown to be following straight line equations or approximating to straight line equations, including one for you physicists out there, Hooke's law. So let's have a look and get started as ever with the warm-up questions. So here they are, 1, 2, 3 and 4. Have a go at these yourselves first and foremost, and then use the video only once you've tried them yourselves, and use the video to help you make any corrections if you need to make any, that is. With a bit of luck, you'll fly through these and might not need to make any corrections. So have a go now. Okay, so we'll have a look at question 1 together. So for question 1, we have a line with equation y equals 3x plus 10. The line L2 is perpendicular to that one and goes with the point minus 2, 4. Find an equation of line L2 in the form ax plus by plus c, where a, b and c are integers. So this should be fairly familiar to us now. So the first thing I would suggest we might want to do is just think about L1 first of all. So L1 obviously has equation y equals 3x plus 10. This writing tablet's going a bit weird sometimes on me, so I don't mean to say minus. Y equals 3x plus 10. Now L2 is perpendicular to that one. Because the gradient of L1 is 3, we can therefore see that the gradient of L2 is going to be the negative reciprocal of a gradient of L1, so it's going to be the negative reciprocal of 3. In other words, it's going to have a gradient minus a third. It also goes through 2, 4, minus 2, 4 I mean. So we can use this form of the equation. We can do y minus y1 equals m brackets x minus x1, because we know a coordinate point and we know the gradient now. So we know the gradient of L2 is minus a third. We know a known x coordinate is minus 2 and a known y coordinate is 4. So if we just substitute in these values and solve, we're going to get y minus 4 equals minus 1/3, sorry about this, minus 1/3 brackets x minus x1, which is minus 2, so it's going to be x minus minus 2. Now we need it in this form ax plus by plus c, where a, b and c are integers. So what I'd suggest we do is just multiply through the whole of this by 3. That's going to give us 3y minus 12 equals minus 1 brackets. Now there's a chance to get rid of this minus a minus, which is almost tempting into making a mistake. So call that x plus 2. Expand out the brackets, so 3y minus 12 equals minus x minus 2, and then we can now rearrange this by adding the x and a 2 to both sides. We get therefore that x plus 3y, and then minus 12 plus this 2 gives us minus 10 equals 0. Question 2, we have two lines that are intersecting at a certain point. We need to find that point of intersection. So there's a few ways of doing this, as almost always are for different elements of maths. What I'm going to do first of all is I'm going to take this equation here and rearrange it so it's y as a subject, like this one is. So if I add y to both sides, I get y equals 3x plus 10. So now both are of the form y equals, I can equate these two expressions for y. So therefore, we can say that minus 4x plus 3 is going to equal 3x plus 10 at the point of intersection. So if I add 4x to both sides, I see that 3 equals 7x plus 10. Subtract 10 from both sides gives me minus 7 equals 7x, and dividing through by 7, we see that therefore x must be minus 1. Now, when y is minus 1, we can just substitute this into this expression here to find what y must be. So, when x is minus 1, y is going to be minus 4 lots of minus 1 plus 3. Minus 4 times minus 1 is positive 4, plus 3 is 7. So if x is minus 1 and y is 7, therefore we can say that p has to be minus 1, 7. And we're sorted. Question 3 is true to real life. There is a set of formulae, two formulas, that convert from Fahrenheit to Celsius and back again. So what follows is true. So this is just a chance for you to derive these formulae for yourself. So it reads, the Celsius scale and Fahrenheit scale both measure temperature, obviously. Water freezes at 0 degrees in Celsius, which is 32 degrees Fahrenheit on the Fahrenheit scale. The boiling point of water is 100 degrees Celsius, and that's 212 degrees Fahrenheit in the Celsius scale and Fahrenheit scale, respectively. So let's try and use this information to derive a formula that changes, first of all, Fahrenheit to Celsius. So let's just think about that. We want to go from Fahrenheit to Celsius. So we want something that gives us Celsius. If that's the case, and we're going from F to C, we want C. In other words, Fahrenheit in, Celsius out. So our input needs to be F, the output is C. And so if we relate that to a graph, an x-y graph, F is going to be along our x-axis, and the output, which would normally be the y-axis, can be our c-axis. So we can set up a problem like this, where c is our new y, and f is our new x. If we just read this carefully, we can add in the information we need. And so, just by reading the second sentence, we see that water freezes at 0 degrees in Celsius, which is 32 degrees Fahrenheit on the Fahrenheit scale. And so F is 32, C is 0. So we can add in that point. Next, it says about the boiling point of water. So we know that when F is 212, C must be 100. So we can add this point in as well. Okay? We also should know, in fact we can assume, and it is true, it's a linear relationship between these two. So now we've got these 2 points. All we need for a straight line graph is to know any 2 points and draw a straight line that goes through and extends past both points. So there's our line that converts F to C. So let's just think about how we can now take this further and generate an equation. Well, one thing we could do is work out the gradient of this line. So the gradient, as ever, is the change in y, or in this case the change in c. So over here it's 100, down there it's 0. So the change in c is 100 minus 0. The change in x, this is now the change in f, is 212 minus 32. And so we're going to have 100 on the top, and on the bottom, 212 minus 32 is 180. Both of these numbers are factors of 20, so that becomes 5 over 9. We can now use a type of formula like the y minus y1 equals m brackets x1, but bearing in mind we're not actually talking anymore about y and x, we're talking about c and f. We can just adapt that as such and say c minus c1 instead of y minus y1 equals m brackets f minus f1, because we know two coordinate points where we know both f and c. And so let's just pick the easier one. What I'm going to suggest we do is to pick this one because it's just easier. Okay, so let's just go for this point here, where f is 32 and c is 0. So c minus c1, which is 0, equals the gradient we just worked out, which is 5/9, then f minus the known f coordinate, which is 32. And we've got it now, because c minus 0 is just c, so therefore c is just 5/9 of f minus 32. And that is the formula that changes from Fahrenheit into Celsius. Now for part B, from Celsius to Fahrenheit, you could do the same thing and change the axes and rearrange and whatever, but what I'm going to suggest we do is we just take the result from part A and manipulate this to make f the subject. So just borrowing from part A, we had c equals 5/9 f minus 32. If we multiply both sides by 9, we get 9c equals 5 brackets f minus 32. If we expand this out, we get 9c equals 5f minus 160. Next, we can add 160 to both sides. So write the 5f first, so we get 5f equals 9c plus 160. Therefore, if we divide through both sides by 5, we get that f must be 9/5c, 9/5 c, plus 160 divided by 5, which happens to be exactly 32. So we've therefore generated the formulae which changes from Celsius to Fahrenheit and from Fahrenheit to Celsius. Question 4. There is a unique point where the temperature in Celsius is exactly the same as the temperature in Fahrenheit, so we need to find this particular temperature. This just coincides with where the lines would meet if you were to plot Celsius and Fahrenheit. So just using one of the equations from before, we could use, for example, probably the easiest one I'd suggest would be that c equals 5/9 brackets f minus 32. But when f equals c, we can say that c equals f, or indeed that f equals c, so we can just equate c and f. We can substitute in place of f, that f equals c. So then what we're going to get is c equals 5/9 c, because f is c, minus 32. So if we expand this out, we get c equals 5/9 c minus 5/9 of 32. So let's just work out what 5/9 of 32 is. So 5/9 times 32, 160/9. So let's just leave it as 160/9. Rearrange, so if we subtract 4/9c from both sides, so if we subtract 5/9c from both sides, we end up on the other side with 4/9c equals minus 160 over 9. We can then multiply through both sides by this 9. We get that 4c equals minus 160. Then dividing through by 4, therefore c, which equals f, is minus 40 degrees. And so if you're in the North Pole and it happens to be minus 40 degrees, it doesn't matter if it's Celsius or Fahrenheit, because both of those temperatures just happen to be the same at that particular point. So minus 40 reads with both on both scales. Reads the same on both scales, I mean to say. Now the main bit of the lesson, modelling with straight line graphs. So let's just run through a few basics on this point. So two quantities are in direct proportion when they increase at the same rate. So just before we get started, if it's a straight line graph, it's not necessarily to say that they're in direct proportion. So the Celsius and Fahrenheit example I gave you is a linear relationship, but they're not proportional. Okay, so I'm just going to clarify what we mean by direct proportion. It means two main things. The first thing is when one quantity doubles, the other also doubles. So like when one halves, the other halves, and so on. If one is multiplied by 100, the other is multiplied by 100. But perhaps the most important point, if it's in direct proportion to quantities, then a graph of them is always going to go through the origin. A graph of direct proportion will absolutely always go through the origin. If it doesn't, the two variables can't be in direct proportion. So here's a graph just showing two variables. Let's just call them x and y, like as standard really. Just a few things to show. So if y is proportional to x, we can write this in a mathematical shorthand as y, and this symbol here, it looks like a bit of a fish almost, x. Now this symbol means proportional to. This is the proportional symbol. So if y is proportional to x, equivalently, it also means we can say that y equals x multiplied by some constant of proportionality, which is often called k. And so if this holds true, we can also say that y equals k multiplied by x, y equals kx. So this could be a graph of y equals kx. So if we just think about y equals mx plus c for a moment, c is 0 because it's going through the origin, because these two variables are in direct proportion, and the gradient m is the same as this k, and so the constant of proportionality is one and the same thing as the gradient. So going back to the very, very basic idea of what the gradient tells us, it means how much the vertical variable changes for every increase of 1 unit in the horizontal direction, in this case the x direction. So putting it simply, the gradient just means if x increases by 1 unit, y increases by k units. So that's what this gradient k is. So the constant of proportionality is k, and it means that if x increases by 1 unit, y increases by k units. Now just a bit of mathematical language for you, which I didn't need to include, but I'm going to include it just to introduce you to a few more symbols. Because y is proportional to x is equivalent to y equals kx, we could write it mathematically like this. Y proportional to x, this double-headed weird arrow thing, y equals kx. Now this double-headed arrow means one implies the other in both directions. And so y being proportional to x implies y equals kx, and if y equals some constant multiplied by x, that also equally implies that y is proportional to x. This double-headed arrow also means if and only if. So if and only if applies to this double-headed arrow as well. Let's have a look at a couple of worked examples. So first of all, worked example 1. This is what I was saying at the introduction. This is one for the physicists. We've got a graph opposite showing the extension of a spring when different masses are attached to the end of the spring. So we can see here that this is a proportional relationship because it's a straight line going through the origin. First of all, we need to calculate the gradient, which we're calling k, of the line. So as long as you pick any two nice enough points, this is fairly straightforward. So the origin is the easiest one to pick, I think, and this one goes through 420 respectively for x and y. So just making that as clear as I can, like so, we can now compute the gradient. So when m is 400, e is 20. So the gradient is the change in the vertical direction. I'll normally say change in y over change in x, but in this case it's change in e divided by change in m. So e has gone from 0 to 20, so k is going to be 20 divided by the change in m, and m's gone from 0 to 400, so 20 divided by 400, that simplifies down to 1/20th. Part B, dead easy. Write an equation linking E and M. So this is a straight line graph, so it's like y equals mx plus c, but just c is going to be 0 because it goes through the origin. So it's just a case of y, if you like, which is actually capital E, equals mx, where m is the gradient, but only here it's k. So gradient multiplied by the x variable, which is m. Or we could put e equals m over 20, either or. Part C, explain what the value of k represents in this situation. So going back to the introduction on straight line relationships, easiest thing is if I just show it to you in writing, so my squiggly, horrible handwriting doesn't put you off. Well, k tells us by how many centimetres the spring extends further by for each extra gram of mass attached to it. So another way of thinking about that is, for every extra 1 gram attached, it results in a further extension of the spring by 0.05 centimetres. Let's have a look at another worked example. This one is about modelling populations. So in 1991, there were 18,500 people living in Bradley Stoke, which is a town. Planners projected that the number of people living in Bradley Stoke would increase by 350 each and every year. First of all, we need to write a linear model for the population of Bradley Stoke t years after 1991. So what we need to do for this one, first of all, is to think about it on a graph here. So we have P and we have T. We now need to add in the information we can on this set of axes. So first of all, we can see here that it says in 1991 there were 18,500 people living in Bradley Stoke. T is the time after 1991. So at 1991, T is going to be 0. And so this point here we could map as being 0, 18,500. This is the p-axis intercept, so we can add this on straight away. There we go. There's also something else where we've been told as well. So planners project that the number of people living in Bradley Stoke would increase. So I'm just going to underline that. So the population we're planning is going to go up. So it's going to be a line going upwards with a positive gradient because we're talking about a population increase. So generally the line's going to be heading up rather than heading down. Next it says it's going to increase by 350 each year. That means for every extra year we go along, the population is expected to go up by 350. And so this essentially is the gradient for every 1 along, every 1 year along, 350 up, another 1 along, 350 up. So we can now formulate a relationship for this population of Bradley Stoke. So P, the population, link it back to y equals mx plus c again. So we need the gradient, which is 350, So it's going to be 350t, so y, if you like. So liken it to y equals mx plus c. You don't need to write this down in an exam. I'm just sort of showing you how it links. So that's our y, if you like. 350 is our m. X is now t, then plus c, where c is the y-axis intercept. Here it's a p-axis, and it intercepts at 18,500. So there we have it. That's all that's all we need to do. So I'm just trying to show you, I suppose, that although it might look new and unfamiliar, we can always link things back to familiar territory. All this is really is just y equals mx plus c dressed up a bit. So that's the relationship linking population and time after 1991. For part B, we've got this model which is obviously very simplistic. Write down one reason why this model might not be very realistic. Now this is a common type of 1 mark question in an exam. You might be thinking, well, it's only 1 mark, it's not important, but marks add up, obviously. This mark might be the difference between a grade one day. So it's important that you're confident answering these little 1 markers that might add up. I'm going to write down sort of what I think in order of obviousness, what you could write down. So any one of the following. So one thing you could say is that the number of people living in Bradley-Stoke, or living anywhere in the whole wide world for that matter, it's very unlikely to increase by the same amount each and every year. 350 is a ballpark figure. It's never going to go up by exactly that each and every year. If anyone thought that, could be a bit crackers, I think. That's just not going to be something you can bank on. Something else you could say is Bradley-Stoke's population can only grow to a certain point before reaching limitations. For example, town boundaries. If it kept growing and growing and growing, eventually the town would start splitting into other towns, and it would no longer be Bradley-Stoke. So you can't use this model forever. It also might be geographical limitations. For example, you might have not enough houses, or they might be bounded by a river or something. Who knows? There's no point thinking too hard and heavy about a 1 mark question, but a town can only be so big. Another thing you might say is that this model, obviously, it doesn't account for unpredictable future scenarios. So anything could happen in the future. So there could be local housing developments, a creation or loss of jobs, which could change the population. People might leave or come in for new jobs, changing levels of birth rate, immigration, and so on. There's just anything you could put as long as it's common sense and a reasonable answer. But I would suggest the most obvious thing to put, always go for the obvious if you can. I would suggest the best one would be that one, instead of thinking of weird and wonderful, strange options for what you could put down. Put something relevant, something that springs easy to mind. Common sense often wins. Just a final thing before we close down the chapter. It's a very little thing. I just wanted to bring to your attention a previous result involving finding the midpoint between 2 points on a given line. Okay, it is a formula. You don't really need to think of it as a formula, but it's something which is worth a little mention, because it won't take me long. So if you have a line segment here, x1, y1 at one end, x2, y2 at the other, we can find the midpoint of a line segment by averaging the x and y coordinates of its endpoints. Simple as that. So the midpoint of a line segment with endpoints x1, y1 and x2, y2 is given by this formula here. All we mean by line segment is technically a line could be infinitely long. So a line segment is just a finite portion of an infinite straight line bounded at either end by 2 distinct endpoints, which we ideally would know. So it's just like a portion of a larger line. Nothing to get too caught up by. So, dead quick, worked example. Using the formula, find the midpoint between these 2 points. It says use the above formula. That's referring to your notes rather than this video. The formula's here, just to remind you. So let's just bang in the numbers, and then we can say we've done the chapter and not missed anything out at all. So, midpoint is going to be x1 plus x2, so minus 3 plus minus 1, over 2. Then y1, which is minus 7, plus y2, which is 2, all over 2. Minus 3 plus minus 1, that's minus 4, so minus 4 over 2. Minus 7 plus 2 is minus 5. So the midpoint, minus 4 divided by 2 is minus 2, and minus 5 divided by 2 is minus 2.5. And that, indeed, would be the midpoint between those two lines. It's a very tiny thing, but I just thought I'd mention it there, just so you can't ever say to me, "Sir, you didn't mention that." Well, I have now, so there you go. No. Now, finally, over to you. This is the last thing we'll do on these straight line graphs. We might recap it at the end of the year, for example, or here and there in space reps. But go to page 106, exercise 5H, try questions 5, 6, 7, 8 and 9, and then mixed exercise 5 for some suggested independent study. Try and just smash out those questions if you can. Again, I sound like a broken record saying the same thing every single time at the end of the video, but please, I do mean it. Ask me if you get stuck. Do not just pretend you're okay if you're not. Keep working hard, keep watching these videos, keep working at home, and best of luck. Thanks again for listening.